Hello everyone, welcome to the course on architectural design of ICs. So, in the last class we have seen the timing that means static timing analysis basics. So, today we will discuss the timing issues in digital IC design and why we have to consider these timing issues mainly if we need, that means the closer to the actual performance timing information about the, that means real time integrated circuit which is comes in the form of that means physical integrated circuit chips. So, if we need that to check the performance of when that is fabricated and we got the black tiny chips. So, how it works, whether all the paths or all these timing informations are correct whenever, because this once we develop this integrated circuit, it really, that means it consists with so many, that means other costs. Okay. So, once if we have done that, so then there is no such options that okay, we will that means remove the error and then again we will redo the things or reprogram the things, so that every timing informations are that correct, so that the digital chips are working fine. So, to avoid that, as in digital integrated circuits there is no such options for the errors. So, that is why whenever we are doing this analysis, so at that time we must have to be very much sure that everything is correct or every path is, there is no such violation, whether that is setup time violation or hold time violation. So, every path meets the timing constant as well as, that means all the other constant which we have already put. So, that whenever it is working in real time, it just actually performs as what we have thought whenever we are just designing it. So, for that reason we have to put the constant to the clock, okay, whenever we are designing this digital IC design. So, what are there, what we should put and why we should put those constant, what is the meaning of those constant, that we will see in this particular lecture. So, we know that in actually in timing analysis we can get two type of timing violations. So, what are those? One of these timing violations actually will be the setup time violation and another timing violation will be the hold time violation. So, now the question is that how to, if I got the violation, so at that time how to fix these timing violations. So, one of the technique is that optimize using the synthesis tool. So, optimize using the synthesis tool means is, this is the easiest of all the other options. Few of the techniques have been discussed in the sections of optimization, that means whenever we have already that architectural optimization, whenever we have already talked about, and few other techniques will be dealt with this later in this particular section. So, mainly this whatever we have discussed, that architectural design of IC, that which is the, that means name of this course, there what we are trying to do, we have tried to optimize the circuit in terms of, that means architectural level. So, we can optimize the circuit in terms of logic levels or in terms of gate levels. So, other optimization options are also there. So, the timing, that means if we optimize the circuit, then obviously there will be improvement in the timing performance of the particular circuit. So, by that also we can fix the timing violation if we are getting any. So, that is why this is the easiest one. Then we are getting, that means the second option is the micro architectural tweaks. So, this is a manual approach compared to the previous one. Here the designer should modify the code to make micro architectural changes that affect the timing of the design. Some of these techniques were discussed in the previous lectures and few ones will be dealt with later in these particular sections. And as well as you know this micro architectural changes. So, that is why we are basically we are dealing with all these architectural aspects where we can improve the performance in terms of area or whether we can improve the performance in terms of timing. Okay. So, this the synthesis tool actually what it does is it does the optimization automatically. So, automatically means, does it means that okay, it is so much intelligent, automatically it can do the corresponding optimization? No. Basically there are some algorithms which are running behind of it. So, depending on that, so who have developed that EDA tool or the synthesis tool, they have put those options. So, if you put the constant to the tool that okay, so this is my area is my major constant, or so power is my major constant, or this speed is my major constant. So, depending on that your constant, which constant you are putting, you are telling the tool. So, depending on that corresponding algorithm will be selected and those algorithms will be applied to your particular code. So, that you can get the best performance by the tool automatically. Okay. So, actually these are the techniques by which you can fix the timing violation. So, in compilation mode you can just, that means if you can put this map effort high, and then you have this, you can group the critical, that means you can identify the critical path, and then you can group them and weight, that means assign different weight factors, so that the tool automatically try to modify those paths to get a good performance. And then you have other options like register balancing, and then there you are having this, you have to choose a specific implementation for a module, like if you are like if you are having this adder architecture or multiplier architecture or subtractor architecture or divider architecture. So, those basically try to modify, or those will try to optimize the circuit in terms of speed, power and area, which we have seen till now in the particular course. And so, these are the other options by which we can. So, now how we can fix the hold violation. Okay. So, the hold violation, for fixing the hold violation, first when the hold violation occurs, that means when the data arrives too fast. Too fast means, actually we have already seen when this hold time violation can occur, again we will see when this hold violation can occur. But the thing is that the best method to fix this path is to add the buffers on the particular path, so that the data comes, or the data that means is delayed. Hold violation basically comes because of it reaches the data too fast. So, if you want to make the data very slow, so at that time you put the extra buffers onto that particular path, so that the data now comes at late and you can fix the hold violation. Okay. So, what is that means this necessity of these buffers? These buffers basically generates as additional delay, slowing the path considerably, and one has to be very careful while fixing the hold time violation, because whenever you are putting hold time violation, so adding these buffers means you are basically again affecting the clock time requirement. Okay. The cycle time at that time it will be more. So, you have to be more careful whenever you are doing or you are applying these techniques, and too many buffers would slow down the signals a lot and might result in setup violation, which will be a problem again. Then why is this timing analysis is very much important while you are designing a chip? Timing is very much important because just designing the chip is not enough. We need to know how fast the chip is going to run and how fast the chip is going to interact with the other chips, how fast the input reaches to the output, etc., etc. Because whenever we have designed this digital chip, so at the time you have to place it somewhere, so that it has to be connected with the real time inputs and the real time outputs. So, for that reason, what its actual performance, that we have to know from the beginning while we are designing. It is not that the simulation and the actual performance, there is a difference. So, there is a gap. So, if you can, that means close that gap. So, your simulation results and your simulation result means virtually you are basically you are trying to check the performance. So, when this virtual results and real time results, they are much more closer to each other. So, at that time you can say that you are that means you have designed or you have developed one circuit which is perfectly fine, or I can assure you that okay, it will work perfectly fine whenever it will be, that means placed in a printed circuit board, or it will be placed for a, or it will be used for a real time application. Then why do we normally do static timing analysis and not dynamic timing analysis? What is the difference between them? So, what is dynamic timing analysis and what is static timing analysis, that we have already discussed. That in dynamic timing analysis we put the simulation, that means these test vectors we put, and then we check every corners of that. So, that depending on the, that means signals level, that means whether that is 0 or 1, depending on that the actual circuit performance also we can analyze that okay, if this signal is 0, then it is working like this, the delay is something like this, or this the net delay is this. So, that we can also do in timing analysis, which is the example of dynamic timing analysis. But in case of static timing analysis, all the information are fixed depending on the which technology library you are using, like this gate delay, they are fixed, this net delay, they will be calculated on the fly depending on the well load model. Well load model means where this resistance and capacitance values are stored. So, depending on this, what is the length, only that information is required, and which metal layer you are using, only that information is required, and depending on that you can calculate the corresponding net delay on the fly, and you get the static timing analysis values. So, the timing analysis can be done in both ways, static as well as dynamic. So, dynamic timing analysis requires a comprehensive set of input vectors to check the timing characteristic of the paths in the design. Basically, it determines the full behavior of the circuit for a given set of input vectors. Dynamic simulation can verify the functionality of the design as well as the timing requirements. For example, if we have 100 inputs, then we need to do 2 to the power of 100 simulation to complete the analysis, and the amount of analysis is astronomically compared to the static analysis. What is the meaning of this? This is that whenever we analyze the timing, that means timing issues with respect of, that means giving the test vectors. So, at that time what is the length of the test vectors? So, 2 to the power of that many numbers test vectors we have to do. That means that much of case we have to consider to analyze the full performance of the circuit in dynamic timing analysis. So, more the number of sets or more the number of variables, input variables, more the number of case you will get in case of dynamic timing analysis. But in case of static timing analysis, as we are not considering any of the test vector on that case. So, at that time the static timing analysis check every path in the design for timing violation without checking the functionality of the design. So, this way one can do timing and functional analysis same time, but separately. So, this is faster than dynamic timing analysis because there is no need to generate any kind of test vectors. That is why ST is more popular way of doing the timing analysis. So, that is why this static timing analysis is much more preferable than the dynamic timing analysis. So, then there are timing exceptions. So, what are those timing exceptions? These timing exceptions are the false path, then the multi-cycle path, then the minimum or maximum path, or if you are having one combinational loop. So, at that time how you can compute the timing analysis of a combinational loop. So, at that time you have to do this, or you have to say, or that means if you are running the circuit in a combinational loop. So, combinational loop where you can find, like in if you have designed one resistors, okay, or if you have designed one flip flop, or if you have designed one latch. So, at that time you will be having one combinational loop. So, the timing analysis, the static timing analysis of that, if you have, that means if you have to do. So, at that time you have to disable those timing acts, otherwise you will get the wrong information about the timing that means timing analysis values. Okay. So, what constant do we put while we do this timing that means calculate this timing that means timing values, or we do this static timing analysis. So, one major thing is that you have to constrain the clock. Constrain the clock means you have to set what should be the minimum clock cycle time or the clock period of the corresponding design what you are doing. Then you have to do this you have to set the input delay as well as the output delay. So, what is that input delay and output delay is that means it is not that you are having. So, if you consider one that means digital chip. So, at that time you must be having the that means the IO pads, they are basically placed little bit far from your core. Okay. So, whenever these pins which are basically connected to the pads, so they need some times to reach to the actual pins of your cores. Okay. So, whenever these times that means the time which is required from the input pad to the input pin of your core. So, that information is you can mention by putting that is input delay, and the same thing on the output side, that means the output pin of the core to the output pad, you can set that as a output delay. Okay. So, if we can assume that okay, one clock should be, the period of the clock is 10 nanosecond, if my input is, that means if the output delay is 5.4 nanosecond. So, at that time the input delay should be 10 minus 5.4, that is 4.6 nanoseconds of time. Okay. So, then what are there whenever we are considering any clock. So, at that time there are few things which you have to know about, which are basically related to the clocks only. The clock latency. So, what is this clock latency? Clock latency means the delay between the clock source and the clock pin. So, this is called as source latency of the clock. Normally, it specifies the skew between the clock generation point and the clock pin. And what I said is that whenever you design one circuit, that means IC. So, at that time your core has the pin. Okay. So, that will be having the clock pin. Now, the full chip will be covered by that input output pads, where these pads will be connected to the real world. Okay. So, those pads are basically there is a gap between those pad pin, that means the pad cell, to your input pin of the core. So, in clock, the clock should be come externally. So, the clock pad, if you are not generating your clock inside of the core. So, at that time the output of the clock, that means the external source of the clock which is coming to the pad, then to the pad, from the pad to the pin of your core. So, it needs some time, which is again it is connected through wires. So, it will be having some of the delay, which is considered as the clock latency. Then rise time. So, it is defined as the time to takes for a waveform to rise from 10% to the 90% of its steady state value. So, as we know that actually, though we have considered the any signals like the transition from 0 to 1 or 1 to 0, there is no such time it takes, that means the instantaneous we consider in ideal case, but in actual whenever we work with the real time signal. So, at that time it takes some times to reach from 0 to 1 or 1 to 0. So, that is why this rise time is basically the time requirement where the waveform takes or the signals basically takes from low to high of 10% to 90%. So, the time which it takes to go from 10% to the 90% is known as rise time. The opposite ones, when it comes from 90%, that means from high to low, 90% to the 10%, that is the fall time. Then clock to Q delay. Okay. So, what is this clock to Q delay? It is the delay from the rising edge of the clock to when Q becomes available. So, it depends on the input clock transition as well as the output load capacitance. Means what? As we have already discussed that the register itself will be having some inherent delay, because it is made by some of the that means gates. Okay. So, those gates will be having some of the delay. So, from the clock to the output, clock is the input pin. So, from clock to the output, how much time it takes, that is the delay of that particular register, which is known as clock to Q delay, and it depends upon the input clock transition as well as the output load capacitance. So, if one particular register is connected to several other loads, so at that time depending on the loads, this particular path will take much time. So, then again clock skew we have already defined, already we have discussed. Again actually if I say that it is defined as the time difference between the clock path reference and the data path reference. The clock path reference is the delay from the main clock to the clock pin, and the data path reference is the delay from the main clock to the data pin of the same block. Okay. Then metastability. Metastability is nothing but a state. It is the condition caused when the logic level of a signal is in indeterminate state, or it is in that means it is in, you cannot recognize the data properly, whether that is 0 or 1 unambiguous state. If you find, then that state is known as metastable state. Then there is another that means important point, which is the clock jitter. It is the variation in the clock edge timing between the clock cycle. It is usually caused by the noise. So, what is this clock jitter? Clock jitter means, suppose the clock is a continuous source, right. So, it is not that every that rising edge and the falling edge of the clock. Suppose clock means I am having, if I consider one particular clock cycles. So, that means whatever is the time period we set. So, from the rising edge to the falling edge, and then again if it is finds the rising edge up to that, that is the clock period. So, if I consider let us say 100 cycles. So, if I that means superimpose them one after another of these 100 cycles, it is, I will not find that every of this rising edge of the clock is same to each other. There will be slight different in the rising edge as well as the falling edge, which is basically caused because of the noise which is associated with these clock pins. So, that is why this basically creates the clock jitter, and as I said that clock is the major component in digital circuits. So, that is why you have to be more careful, more cautious while you are designing with, or you are playing with the clock in the design. So, then again setup time and hold time, this we have already discussed. The time requirement before the clock edge arrives, when the data must be stable, that is the setup time, and the hold time is the when clock edge arrives. Then again still we need some times to properly recognize the data. So, that time is the hold time. Okay. Now, then again actually if we consider one of this, that means two flip flops, this is the basic consideration of any that means digital circuits, that there will be two registers and in between of them there will be the combinational logic, which defines this, the maximum critical path of this will be defined the clock, that means the minimum clock period requirement of these two registers. Okay. So, apart from that, not only this, we have seen that the T setup plus the skew plus the hold, all this basically constrain the minimum requirement of the clock in this kind of circuits. Okay. So, now whenever we are doing, suppose this is the case if we consider. So, this is flip flop 1, this is flip flop 2, and in between we are having some combinational logic, and both the clocks are basically driven by one single clock pin. So, at that time if we have to do, or how we have to do this setup timing check, is that this is my clock, okay, this is my clock source. So, if these two particular flip flops are positive edge trigger flip flop, so at that time whenever I find this clock edge at this clock, at that time this is the input data of the flip flop 1. So, if it is this is known as launch edge. So, launch edge will find that okay, the data input value is 1 over here, and after that, so I will get the output at q after some time. Why after some time? Because this is the requirement of this clock to q delay we are having for this flip flop 1. Okay. So, then this the output of the that means flip flop 1, that will be the input to the combinational logic, and then again after that it will be the input to the second clock. Okay. So, sorry, second register. So, this now will come over here, that means this will come because of the combinational logic delay if it is arrives here. Okay. And then again for the next for this particular clock, now what will happen in this edge both the flip flop will try to find what is the value of its data. So, in this particular case the data for flip flop 1 is 1. So, that is why this flip flop 1's output comes over here, and as the this q is 0 over here at this edge for the this. So, at the time it will consider to continue to 0. So, this will come at this particular time, then again at the next clock edge it finds that okay, this flip flop 1's data is 0. So, again it will be after some times it will come down to 0, and here at this particular case the input of the flip flop 2 is 1. So, it will be again it will be goes to 1 after some time. So, this particular requirement, this delay is coming because of the clock to q delay. Okay. So, then this is the actual arrival time and this is the required time of the data which will be coming. So, the slack amount is the that required time minus the actual arrival time is, if it is positive. So, at that time I can say that okay, the design will work perfectly fine. Okay. So, this is the how actually in circuit or in static timing analysis we do the setup timing check, or the tools, actually not us, the tool automatically performs the setup timing check while it does the static timing analysis in the circuit. Okay. So, this is the basics or how this tool works when it runs the static timing analysis on the corresponding digital circuit what we have designed. So, for today this is it. Next day again we will consider more on these particular aspects. Thank you.